So, ladies and gentlemen, dear colleagues, let me start a group of talks called CIIRC Annual Colloquium on Research Results. Today we have the second round, and the objectives are very clear, just to inform other people about the best research outputs in 2020. And we are recording these talks, so if there are no objections from the speakers and heads of department, we will put the resulting video on YouTube someday later, so that it is available to wide public. As far as for organization, the program spans today and tomorrow, as you see in the PDF on your slide, hopefully. And we have always afternoon program starting at 1 p.m. And each head of department will manage his or her time slot and will be responsible for finishing on time. Therefore, every speaker should stick on the schedule, and there will be like one question only after each talk. This will be managed by the head of respective department. And now let me ask Professor Mařík to introduce Department of Intelligent Systems and to introduce and manage his speakers. Okay, the floor is yours, Professor Mařík.
Thank you very much. Good afternoon, ladies and gentlemen. So the first part of this colloquium is dedicated to Intelligent System Department. But at the very beginning, I have to stress that the Intelligent System Department, which has been already very big, will be split since May into two departments: Intelligent Systems and Artificial Intelligence. So the first hour of the colloquium is dedicated to the results of the Intelligent Systems part of the Intelligent Systems Department. The second one will be managed by Josef Urban, and there will be results presented by the Artificial Intelligence part of the Intelligent Systems Department. I don't want to make it very complicated, but as a matter of fact, the Intelligent System Department has got several centers and several groups, and we will present results, not the structure of the department today. So what we were asking for was clear presentation of results which were achieved in 2020 by individual groups or teams. And I think it's the best way simply to present results instead of structures or organizational issues. The first presentation will be dedicated to very successful conversational system Alquist 4, and the presentation will be given by Jakub Konrád as a representative of the team of Jan Šedivý and others. So I would kindly ask Mr. Konrád to start and to stick with the time schedule.
Hello, thank you. Let me just quickly switch to sharing the presentation. I think you should be able to see it now.
Yes.
All right. Thank you. So I am going to talk about the results that our team has achieved in the previous year. We are working under Pan Šedivý as a part of the Intelligent Systems Department, and our focus is on the way the intelligent systems communicate with each other and how they communicate with their users, and specifically how they communicate in natural language and how they communicate via voice. We've been part of the Alexa Prize competition, which is an international competition held by Amazon for 4 years now. And what the competition's goals are is that the competition focuses on having a natural language conversation with the user for about 20 minutes. which is a difficult task. And in order to achieve it, the system has to focus on the preferences and interests of the users and the topics they are interested in. It then has to gain some external knowledge about these topics from outside of the system and to introduce it in the conversation. And finally, with the recent boom in the neural response generation caused by the utilization of self-attention models and transformer-based architectures, the new field is flourishing in the conversational AI, which is end-to-end system based solely on the neural response generation. What that means is you have a system that you give a sentence in a natural language, and it outputs a response to that sentence also in natural language. So those are the three topics I'm going to be talking about here. Here is a quick overview of the systems. I'm just going to mention that I'm going to be primarily focusing on the knowledge graph part of the system and on the natural language generation part of the system. But you can see the full overview of the system in our papers. Firstly, let's talk about the knowledge utilization. As I said, it is very important to be able to utilize knowledge from the conversations with the users and to utilize external knowledge to then introduce to the users during the conversation. Which is why we have created custom ontology that is able to hold all the information that user mentions during the conversation. You can see that we have some simple fields like name of the user or their hobbies, but we are also able to hold and we are focusing on holding named entities in this ontology. And specifically, we hold a named entity here, for example, the movie Matrix in the ontology, and then we link it to other publicly available external databases that allow us to add more information to the conversation that is not anywhere in the system, but instead we are able to access it from outside. This creates another issue that we have been able to resolve, and that is that this information is often presented in a structured form. So you have a triple that is, for example, the actress Emma Watson, that you have the predicate of the triple, which is place, and that you have the object of the triple, which is the name of the role, for example, Belle. But you have to create a natural language sentence from that. We are doing that by utilizing two approaches, an LSTM network and a transformer-based architecture. The reason why we've selected these two is because the LSTM performs better on a data that is more highly present in our training data, whereas the transformer is able to generalize better, and so we switch between the two based on the problem. And the result of such system is we have an input that is two triples. One is about the Emma Watson and Belle, and the other is about Belle and the movie Beauty and the Beast. And from that, the system is able to create an output that you can see on the screen. Emma Watson played the role of Belle in Beauty and the Beast. And this way, we are able to basically introduce an external knowledge to the conversation and enrich it and make sure that the user is actually interested in what we are talking about, and we are not just rehashing of what has already been said. And finally, I'm going to talk about the neural response. We are using two models. We are using we are using a model that is called the GPT, Dialog GPT, that is based on GPT-2. And here you can see the example of how this model performs. So, for example, user says something about Nintendo. We find some information about Nintendo on the internet, but we don't really know how to successfully plug it into the conversation, which is where the neural response generation comes into play. And bot generates something like, speaking of Nintendo, have you played Pokemon? The user continues with the conversation. we continue with the neural response, and then we finish by returning back into our current system. Here is the schematic representation of such dialog structure. We have the neural response generation, and it first prompts the user for some reaction, and then it concludes the statement and returns back to the pre-prepared content of the bot. And finally, I'm going to talk about achievements of the team. We have been selected to participate in the Alexa Prize competition 4 times now. We are currently participating in Alexa Prize competition 4. And we have placed twice on a second place from the selected teams and from more than 100 of teams that were trying to participate in the competition, and once on a third place. That is all from me. Thank you for your attention.
Thank you very much, Mr. Konrád, and please switch on your camera for at least 1 minute. And there is a space for one question. Who wants to put the question? Yeah. So nobody wants to put the question. So Mr. Konrád, thank you very much.
Thank you.
Next speaker is Radek Škoda. He will talk about very important device or solution which was invented by the team of Dr. Škoda, and I think it's your turn.
Thank you. I'm going to share the presentation, so hopefully you're gonna see what I'm showing. Just please confirm that you see the first slide that says Teplator.
Yes. Yes.
Yeah, so I'm going to present something which is something like an outlier here in CIIRC, because it has little to do with robotics and intelligence, but it's a very ingenious development that we do together with the University of West Bohemia. Of course, here I have only our logo, but half of the team is over there and half of the team is here, and there are roughly 12 people doing it. I'm not going to show you the papers that we presented. We opened the project for the public in September last year, when we had several presentations at the Nuclear Engineering Conference in Slovenia, and since then there's some public and PR attention to the project. You might have noticed it's happening on the Czech soil and also in international media. It's been also published last year in the International Atomic Energy Agency booklet, where all the projects of this kind are summarized. So what is it, Teplator? Well, it's a new word, and that combines together Teplo and reactor, Teplo meaning heat. So Teplator is definitely the reactor which is designed to produce heat. And it's designed to produce heat for district heating applications, which are quite numerous here in the Czech Republic and also in the neighboring countries. And right now, actually, we're speaking to almost all big district heating companies in the country. And most of them, I think with the exception of one, they're showing very reasonable interest in the topic. What is it about, and what I'm going to very briefly speak, the concept, how the Teplator is designed, how it's using the spent nuclear fuel. SNF stands for spent nuclear fuel. Basically, that's something that everybody's worried about these days, and how it can be using the slightly enriched uranium, which is the fresh fuel, which is much cheaper than the fuel which is used nowadays. Some few words about the physics behind. I know that this forum is too short for it, but definitely I will just give you the gist of it, what's happening in there, and where we stand in the conceptual design. The theory behind it is rather simple. In the normal nuclear power plants, you have the fuel. So this is the fuel of the VVR plant we have in Dukovany. The fuel, in the form of fuel assemblies, goes into the reactor, and it produces heat and electricity, and that's where the plants generate money. Then the fuel, after several years in the reactor, normally would go to the spent fuel pool and then into the interim storage, which such a building with a lot of cask, or if you want to call it barrels. And then what we're saying instead of taking the fuel directly underground, we put in there a device called Teplator, which can use the energy stored in the fuel, because the energy energetical reactors are using only roughly 5% of the energy, and we can use it in the Teplator to produce heat for district heating. We are not destroying the fuel. We are not vanishing it in entirety. What we're doing, we're using the waste for other heat production, which gets nicely in the very modern concept of a circular economy. Of course, after you use the fuel in Teplator, you still have the fuel, so you do what you were supposed to do with from the beginning, but obviously you generated some money in the process, and you generated the heat with no CO2 production, with no emissions. I don't want to say it's cost-free because you have to build the device, but definitely the fuel is coming almost for free. If you don't happen to have the spent fuel, you can also run it on the fresh fuel, which would give you always a better price than the gas. But of course, then you are not doing the recycling or reuse of the fuel, but you can do it. The concept as such is rather simple. What we're building, we're basically building, somebody can call it a big boiler, or basically the heating pot where you heat the primary medium, which is the water. Then we have the intermediate circle where you can store the energy in the energy storage device, the heat accumulator. Some of them, some of the experiments you can see in the cellar of CIIRC, where we run some experiments with the molten salt. And then you have to connect it to the already existing district heating stations, which basically every city in the Czech Republic above 50,000 inhabitants has some form of district heating. So the demand is rather large. There's a lot of calculations and a lot of physics that's behind. I will just mention two of them, which are most difficult. One of them is just calculating what's happening with the spent fuel, which is already in the nuclear power plants. And over there, we have to calculate basically day by day what's happening with the fuel in terms of the enrichment, in terms of the content of all isotopes. So basically, we're taking the entire Mendeleev table of elements and we're calculating the isotopes day by day. And we need to be sure that the fuel is A, safe, and B, that there's enough energy in there to take it out. Also, in the end, we need to assure that the limit for disposal in the final disposal facility is not breached. So basically these calculations, if I take it in the real terms, there are many months of several clusters basically running the simulations and doing the calculations. Well, after this, we are pretty sure it can be done, and it's been confirmed by reviewers of the papers that the solution is viable in terms of the physics. The other problem, how to do it, is that once you take the spent fuel, you have to put it in a special configuration and with special materials to reignite it again. Sometimes I say it's like if you take ash from burning coal and you're trying to reignite the ash, that it would produce energy again. In order to do it, we have to use special materials. We're using graphite as the moderator and heavy water as moderator as well. And you have to optimize the pitch, meaning how far apart you put the fuel assemblies that the reaction would be running. Here I show just one calculation that shows the difference between heavy water, which is in the red on top, and blue, which is light water on the bottom. This one results in the fact that in the Teplator, you're coming up with a device which is slightly more bulky because you need to put the fuel assemblies more apart to get the energy out from the system. Yet again, these calculations are not trivial, and we had to develop some codes. For instance, UWB1. There's a fast depletion code that we developed together with the Pilsen guys in order to do it. Well, once you do all these calculations, then we were coming with the design, which is basically coming on the left, that shows the channels. In each channel, you have the fuel assembly, and they are spaced apart and moderated with heavy water. And once you do it, then of course you have to play with the design, how you regulate it, how you change the reaction over time, how you have some control elements in there. Again, there's a lot behind which can be discussed if some of you is interested. And this is the design how it looks like today from the top. So 55 fuel channels, each of them having one a spent fuel assembly from the Dukovany plant, surrounded by graphite, and in between the fuel channels you have heavy water. These 55 channels you connect with the pipes. With the primary circuit, we have 3 subcycles with 3 pumps. So the red ones are the 3 circulation pumps. That's still the view from the top, and that's view from the side. So basically, the pumps would pump it up on the top to the heat exchangers, and that's where you take the energy out for the user. Well, we are in the stage of the conceptual designs and designing some sub-elements of it and speaking to the big heating companies, not only in our country. Definitely, that's something that raises interest on all sides. Also, we have some reaction from the green and ecologic parties, some reaction from the guys that are burning coal. Right now, we're running with the device that we call it a demo, that's 50 megawatt device with 95 degrees C temperature, and we are ready to go up with temperature and power as well. As I told you, and that's my last slide, it's been accepted by the international body, the International Atomic Energy Agency, in the booklet of small modular reactors, and you can see we are there just between the French and the Chinese reactor on the top. The kind of unique feature is that we are only 2 reactors here that are designed for producing heat. All others are for electricity, and that's the feature we try to distinguish ourselves. And I think you will see within a span of a year how successful this one would go in reality. So thanks for the attention. I'm ready for the questions.
Thank you. So there is a space for one question. Okay, who wants to put the question? I can see raised hand, but I don't know who. Mr. Křemen, yeah, please. Yeah. Microphone.
Yeah, we can see you, but we cannot hear you.
Okay, is it better now?
Microphone, yeah.
Yeah. This is great. Thanks for excellent presentation. I have just one question regarding the application and quality management system. What kind of risk management did you guys take in the design control of your system? I don't think I saw something like that, but I saw, like, you know, all these things in the reactor. I guess if something goes wrong, you know, there must be some risk management, how to cope with these stuff.
Yes, we take this issue very, very seriously, and basically there are 2 approaches. One is that we're trying to have everything in the passive inherent mode. For instance, if you shut down, the heat is transferred out in a passive and inherent mode. There's one approach which we do quite in depth, and the second one is called the defense in depth. Which basically we're taking redundant features. For instance, we have 3 pumps, and we know that if one of them goes down, we are still able to run it with 2 pumps. And definitely you need to have backup systems and some safety measures. Otherwise, it wouldn't get approved, because in the end it has to be licensed and approved by the government body.
Does it have to comply with some norms? Like what norms are?
Definitely, we have not only international norms which are given by the IEA, but also on the Czech side we have something called Atomový zákon, atomic law, and it has to stick into it, and it has to fit into its categories. So you cannot just come up with a design of any shape.
Awesome, thank you.
I would like to thank Radek Škoda for his presentation. Next presentation will be given by Martin Macáš with the title CIIRC Machine Learning for Statistical Process Control in Škoda Auto. So I am asking Mr. Macáš to start. And
okay, course, thank you very much.
Switch on the camera.
Okay, I hope you can see me now. You can hear me?
We can hear you, we cannot see you.
Okay, I'm sorry, I don't know if my camera works, but I will, yeah, maybe now. So I hope you see the presentation as well. So good afternoon, everyone.
Now it is okay.
Yeah, thank you. Good afternoon, everyone. My name is Martin Macáš. I will present my work together with COCORR, or our work, which is focused on statistical process control and using machine learning on that. First of all, we have a strong motivation, or Škoda, or all factories that are close to Industry 4.0 paradigm need to handle a lot of data and perform quality assurance based on those process data and so on. So there's strong motivation. If you cannot control the quality of your production, obviously there are associated costs and some other problems. So it's well motivated, and really Škoda car and also any other factory needs it very, very much. On the left side now you can see an engine head, which is part of the car engine, and you can see a quality characteristic that we can measure on this part, on this piece. On the right side you can see the values of this characteristic over the time, and there's not just one characteristic. Škoda in its measurement center for one operation only, which is part of production of the whole engine head. Škoda measures a lot of other variables. Approximately for this operation, which I will speak about, it's more than 700 variables, so we have very high dimensional data. And then in such a case, the task of performing a control of the process, of production process, is quite difficult, can be quite tricky. So statistical process control and monitoring flowchart is here. The input is the part which is somehow processed by some previous operations. It goes to the current process, which can be, for example, or it is CNC machining or some other things. And this process creates multiple entities on the, like, holes, surfaces and other things on this engine head. And from time to time, according to some sampling plan, some of those pieces are taken and measured. So I mean the big number of those characteristics is measured using coordinate measuring machine. And then those values, those variables are processed, and the task is to detect if the process is okay, if it works normally, or if there is some problem. We call it out of control state. If there is a detected problem, an out of control state, then a message is sent typically to the production operator, who tries to diagnose it or tries to find an assignable cause which caused the problem, and selects a control action in terms of, for example, some form of maintenance, tool replacement, or tuning of coordinate systems and other things. And in this way, there's a control loop which controls the production process and controls actually the quality or variability of the process. So the objective of statistical process control is clear. It's to detect the occurrence of assignable cause or process shift and to detect it in advance or very soon, because otherwise many non-conforming units can be produced and it can be a problem, and it can cost money actually. This is an example of another process from bottle filling industry, where in food industry they measure just one variable, which is, for example, weight of a bottle. In pharmaceutical industry they can measure, for example, hardness of tablet and so on. In that case, it's just a univariate statistical process control. In that case, a very typical approach is that you model the in-control process, so a process that is okay without problems. You model it using some probability distribution, and then you sequentially check if your new observations are coming from this in-control process or not. If not, then there's alarm and positive detection. And as I shown you, the operator reacts somehow on this positive detection or alarm. Here you can see a typical case where the variable is normally distributed, but it's not always. A common method is that you estimate, for example, parameters of a normal distribution of data, and then you set some boundaries that are called control bounds or control levels, so that the probability of false positive rate, or sorry, the probability of false positive alarm or detection or type 1 error probability is very, very small. So the main goal is to control the type 1 error probability, which you can do, for example, if you have the normal distribution by putting the bounds to ±3 standard deviations. In that case, the type 1 error is very, very small, like 0.0027, which is normal in a so-called Six Sigma approach for quality control and assurance. So
1 minute left.
Oh, okay. In case you have multiple variables like here, you get two problems. First of all, if you have, for example, mutually dependent variables, then it can happen if you, for example, use such univariate approach. You get a control area which is like a rectangle here, and if you have some points which is like this, then you have false negative detection. So this is one problem. Another is that if you perform this testing independently on each variable, then you get high false negative rate because of multiple comparison problem known from statistics. A solution of this is using of multivariate SPC, which we use. And this is one typical example, how to link T-square control chart, which uses something like Mahalanobis distance or something similar, and puts a bound on this, and this creates a control area which is like here, elliptic. But in case you have a not normally distributed data, then you get two problems. And in Industry 4.0, you have a huge amount of variables, and you with increasing number of variables, it can happen very quickly that you violate normality or other things. So that's why in our approach we use machine learning. Here is an example of support vector machine classifier, one class classifier, which is used in anomaly detection, and you can see that it's much better and more natural model of the data. There are many other problems like correlation between variables I already mentioned, autocorrelation, dynamically changing processing, missing values in data, and too many variables, which is the curse of dimensionality problem. And all of those problems are becoming more critical with increasing number of variables, which is natural and will be natural in Industry 4.0 area. We believe that SPC is very important for Industry 4.0, and especially SPC for highly multivariate and dynamically changing processes will be very critical and crucial in future. And now I would like to show just a CIIRC app, which is actually in this flowchart.
No, I have to stop you. Okay. Your time is over. Unfortunately, we are losing time. So thank you very much for your presentation, and the questions can be put directly to Martin. We have no space for any question. Next speaker, thank you very much. Next speaker is Professor Aleš Procházka. Computational intelligence and digital signal processing. Please, Professor Procházka, go ahead.
Thank you very much. I hope that you can hear me. I shall speak about computational intelligence and digital signal processing. I'm honored to speak about this topic that will be published in May in IEEE Signal Processing magazine. We were asked to prepare this presentation that is in some way based upon ideas of Leibniz. Too narrow specialization of scientists makes it harder to understand each other. It seems that digital signal processing is an integrating platform for diverse scientific areas. We saw today already that we are analyzing various signals from accelerometers, camera systems, and so on. Similar mathematical methods include Fourier transform and so on, but there are diverse applications based upon this similar mathematical method. Our studies were related to motion detection using RGB and depth cameras, spectral analysis, digital filtering, and correlation of spatial and biosignals. Bayesian methods can be used for analysis of Parkinson's disease, analysis of data sets of controls. But just now, one paper was published in IEEE Transaction of Neural Systems, devoted to analysis of accelerometric data. It was interesting to see that position of accelerometers was very important. In case that accelerometers was in spine position, it was possible to distinguish a group of individuals with ataxia from healthy persons using spectral methods. In this paper, we used standard methods for classification. But recently another paper was published in Neural Computing Applications, and we used deep learning. And it was very interesting that no features were selected, and all values transformed in spectral domain were used for this analysis. Sleep stages detection is also another interesting topic based upon variables measured by depth cameras and so on. You can see how some results that were published in the last year in Sensors. Of course, pre-processing is very important. Wavelet transform can be used for decomposition, thresholding, reconstruction to obtain denoised signals. EEG signals can be analyzed to obtain spectral features, age-dependent features, and also correlation between musical background and cognition. It was another interesting topic of our research. Sport activities are very interesting for students as well. One of our colleagues was cycling across South America, and with GPS system and heart rate sensors, and we analyzed also here uphill and downhill cycling, accelerometers, spectral components, and classification using this data and using deep learning methods. We can see just now result of this classification published the last year in Neural Computing and Applications. Thermal cameras form another interesting topic with many methods related to signal processing, but not also in biomedicine. We use this method also for engineering to analyze room temperature in various situations. Another application is in stomatology, 3D scanners, and the last year one paper was published related to diffuse reflectance spectroscopy, reflectivity, and analysis of healthy and unhealthy tissues. Here we can see some keywords related to methodology and to applications. Thank you very much for your attention.
Thank you, Professor Prakaska. And now there is a space for one question. Who wants to put the question? If there is no question right now, I would like to thank to all 5 presenters, and our first block of talks is over. I am switching back to Zdeněk Hanzálek to listen to the following block of presentations.
Okay, Vladimír, thank you. So let me ask Josef Urban to follow, okay?
Can you hear me? Can you hear me, Zdeněk?
Yes, I do. I hear you.
Yes, I hear as well. Thank you.
We see your slide, right?
Okay, good. Can you hear me also, Zdeněk?
I hear you. Yeah, it's okay.
Okay, very good. So thank you. This is the first time we will present as a separate department, as Professor Mařík already mentioned. So this is one slide about the newly created Department of Artificial Intelligence. There will be 4 groups led by Robert Babuška, Mikuláš Janota, Tomáš Mikolov, and me and Martin Suda. And there are about 5 tenure track people and about 10 researchers altogether, and about 20 people with the Ph.D. and master students. Let me see if this works. This is the overview of publications for 2020. So there are about 30 publications, mostly in conferences, typically in some AI or more specialized AI conferences, some of them in journals. So without further ado, let me switch back to the Teams and stop presenting and give the floor to Barbora Hucová, who has the first talk. Barbora, can you share your slides and switch on your mic and camera? Yeah, we can see the slides.
Awesome. Can you also hear me?
Yeah, we can hear you.
Great. Okay. Hello, everyone. I will present a paper that I wrote with Tomáš Mikolov, which got published last year, and it's called Classifying Complex Systems Based on Transients. So, okay. So far, it seems to be an extremely hard problem to design a system which would possess some truly general artificial intelligence. But one of the reasons for that is that so far we are unable to formally define what exactly intelligence should be. So the approach we decided to follow is to work with the assumptions that, for example, human beings are intelligent organisms and that they were produced by a process called biological evolution. And what we would like is to come up with some artificial systems which would model some form of artificial evolution, for example, in some software environment. And we would hope that such artificial evolution process would produce some structures possessing the artificial intelligence. But now the problem is how to define artificial evolution. So for us, that's going to be a dynamical systems where structures emerge and further grow in complexity in an open-ended manner. So what we deal with in this paper is the question how to measure complexity of a dynamical system objectively. So the dynamical systems we study are discrete in both space and time, and famous example are, for example, cellular automata. So you can imagine a cellular automaton consisting of a square grid in 2 dimensions, where every square can be in some finite set of states. So, for example, the states could be a black or a white square, and the state of the square changes based on a local rule of the states of some local neighborhood of each square. And this local update rule is identical for every square as well as the neighborhood, and all squares are updated in parallel in discrete time steps. So this is a very simple description of a very simple system, yet the behavior we observe, they are very rich in their dynamics. And for example, here you can see some local structures forming and then reacting one with another. And the question is, how can we objectively measure how complex a certain system is? So we have tackled the problem by designing a novel classification, which we call the transient classification. And I'll briefly explain the main principle of it. So we will only consider cellular automata to work on finite square grids. And because the number of states is also finite, every configuration of the grid forms a the set of all configurations is finite. And if we watch the simulation of some cellular automaton, we know that the simulation will eventually enter a loop. And we just call the pre-period of this simulation the transient part of the simulation. And we can imagine the transient being the part where the information from the initial configuration is processed in some irreversible manner in the cellular automaton. And thus we can view it as we can view the transient as a computation time of the system. And then the loop is just the memory unit of the system. So basically we try to measure the average computation time of a given cellular automaton for a given grid size. And we do that for grids of increasing size to obtain the asymptotic growth of the average transient length. How we do the measuring is just by randomly generating initial configurations, simulating them on a computer, and counting the transients. And we do that as many times to get close to the true average as we can using statistical methods. And so the results, here you can see some snapshots of the cellular automata dynamics. And here are the graphs of the average transients that we've measured. This is the increasing grid space, and this is the average transient length. And surprisingly, for most cellular automata, we would obtain some clear asymptotic growth, which can be fitted to a very simple functions using linear regression. So it's either bounded growth, logarithmic growth, linear growth, or exponential growth. And these growth correlate with the dynamics of the systems very well. For example, cellular automata with logarithmic transient growth tend to die out very quickly and be in this ordered regime where nothing's moving. The linear growth shows some complex structures forming, and the exponential growth correlates with some chaotic behavior with no structures at all. And so thus we have obtained some formal classification of the dynamics, and we have measured many complex cellular automata that are already designed to see that they all belong to the linear class, which made us form a hypothesis that complexity and the linear growth are somehow correlated. We have used this to search, to automatically search through large spaces of cellular automata and filter only those systems that have linear growth to find systems with some intriguing behaviors. These are some examples of systems that we have found in this way. So to conclude, we have come up with a novel classification of discrete systems based on measuring their asymptotic transient growth. And the general trend which we have observed is that logarithmic growth corresponds to some ordered phase of the system, exponential growth corresponds to some chaotic phase of the system, and in between we have identified a region corresponding to some phase transition where complex behavior can occur. Thus, we have some new theoretical results about complex systems dynamics, as well as a new practical tool for automatically searching for systems with complex behavior. And as our future work, I am working on applying the classification to other dynamical systems such as neural nets or Turing machines, and also to use the method to search for hyperparameter values such as the dimensionality of the cellular automaton or its number of states, which would correspond to the critical region where complex behavior occurs. So for example, the result would be that two-dimensional cellular automata with 10 states and a specific neighborhood produce the largest amount of complex systems because they correspond to some phase transition in this large hyperparameter space. And that's it. Thank you for your attention.
Thank you. We have time for 1 or 2 questions. If you have a question, please go ahead directly. Okay, I don't see any, so maybe a question from me. Do you have some faster growth than exponential? Can you do super exponential or Ackermann, or your setup is not like big enough for that?
I would need some like tremendous computational power to be able to measure that. So I have also encountered systems which like max out because I didn't get enough data points to be able to classify their dynamics. They are about like 7% of what I've sampled from huge spaces. So there might be, but I won't be able to tell by this method, I would suppose.
Okay, we need more computers. Okay.
Yeah.
Thank you. So thank you, Barbara. Then, so thanks a lot, Jan. So our next speaker is Mikuláš Janota, speaking about sub-based encodings of optimal decision trees with explicit path. Mikuláš, please go on.
Hi, can you hear me?
Yes.
And you see my slides, I presume?
Yes.
Good.
Yes.
Okay. So hello, everyone. So I'm happy to present the work that I did last year with my colleague Antonio Morgado from Portugal. And so the task at hand is synthesizing decision trees. And we're using SAT solvers for that. So normally in our group, we are actually improving solvers, but in this task, we're actually using them. So every now and then we're actually applying the solvers that we developed. So, so just a quick recap, what are decision trees? So I'm sure you're familiar with the task. So we're given some set of samples and some expert labeling. So some classification, let's say yes, no. And the task at hand is to come up with a decision tree that will tell us how to decide in the future so that it matches on the previous decisions made by the expert in the past. So the question is, what kind of decision trees should we come up with? So what is the synthesis task actually? What's the focus of the synthesis task? And the answer is Occam's razor. So we do want trees that are small because small explanations are good. But what does it mean small? So either we can talk about decision trees that are small in the number of nodes, but we can also talk about the depth. So less deep, so more shallow trees will have less specialization. So both of these criteria are valid criteria to be concerned with. And in this work, we're interested in calculating provably smallest decision tree. And for this task, we're using SAT solvers. So what are SAT solvers? Satisfiability solvers. So the task that SAT solvers can solve is decide things in Boolean domains. So where things are either true or false. So consider, for instance, this small tiny rule that says that whenever the sprinkler is on, the grass must be wet. And then we can ask the questions, for instance, can the sprinkler be on and the grass dry at the same time? And under this rule, the SAT solver says, no, it's not possible. But I can ask a different query. So for instance, can the sprinkler be on? Can the sprinkler be off and the grass wet at the same time? And the answer is yes, because it might be raining and the grass is wet because not of the sprinkler, but of the rain. But it's important to stress that nowadays SAT solvers, modern SAT solvers, are not just for these simple academical toy problems, but they can really solve problems with millions of degrees of freedom. So here we're using SAT solvers to design decision trees automatically with the focus of coming up with small trees. And how do we do that? Well, we pose to the SAT solver the question, is there a tree of size n for the given data? And either the SAT solver comes back and says, well, yeah, there is a tree of size n and we're happy, or there isn't such tree and then we have to try different n. So one natural strategy is that we check if there's a tree of size 1, 2, 5, 7. So we increase the size until we find the tree, the smallest tree that conforms to our data. Now you might ask, where's the science in this paper? So if we're just calling a SAT solver, what's the contribution? So finding a good encoding for the SAT solver is art. So it's difficult to come up with a good encoding. And what we did in this work is that we represent explicitly the paths of the tree. So rather than reasoning about the tree, as a graph, we reason about a set of paths, which lets us control very well the depth, right? So if you remember, one of the focuses was to limit the depth of the synthesized tree. Okay, so this is roughly what we do. And last, the question is it worth pursuing? So is this task worth the effort? And the answer is yes. So here is a small example. So on the left-hand side, you see a tree that was designed by some standard machine learning package that is just using some heuristic approach to come up with the tree. And the tree has 37 nodes and the depth is 11. So it's more likely to be, overfit. Whereas the tree that we are able to come up with has only depth 6 and 29 nodes. Right, so it's much smaller, and the depth is much the tree is much more shallow. Of course, we pay for higher CPU time, but if we're really interested in the smallest tree, we're able to do that. Okay, so that's all for me, and I'm happy to take questions. Thank you.
Thanks a lot, Mikuláš. We have plenty of time for questions. Feel free to ask. Nobody? Okay, so I'll go first. So this is very interesting. I'm curious, like the machine learning people who design these toolkits, they obviously also have all sorts of heuristic methods that protect against overfitting. Do you have any measurements or insights of how their methods compare with your methods when it comes to overfitting?
Yeah, I have to say we didn't do these experiments, and this is definitely something what we want to do in the future. To what extent if really the shallow trees really overfit less. So this is something I think this would be interesting, even if this method would not be used generally in practice because it's more expensive. It would give some sort of a measure of how much more we're paying for doing the greedy methods, right? So essentially, all the machine learning for decision trees is greedy, right? So there's nothing. So they just pick one node to split on next, and it's just done in a greedy way, whereas the SAT solver does it in a complete way. Right?
Mm-hmm. Yeah, thank you. Any other questions? No. So let's thank Mikuláš again, and we will move to the next talk, which is by Lasse Bladbruk. Lasse, are you there?
Yes, I am. Okay,
can you share your screen and your camera, if possible?
Yes. Can you see my screen?
Yeah, I can see that.
Okay. Yeah. Good afternoon, everybody. I'm Lasse, and I will be talking about Tactician, the Tactician system today. And because we have so little time for questions, I basically made the whole talk my imagining you asking me the most relevant questions. So the first question is, what is Tactician? So Tactician is a machine learning technology for the COC proof assistant that helps people write theorems in it. And then the next question you will probably have is, what is a proof assistant? Proof assistant is a tool to help people develop formal mathematical proofs. So if you have some paper proof that you have, but you're not very sure about the correctness, then you can ask the COC proof assistant whether or not it's correct, by interacting with it. So it is a human-machine interactive collaboration system, and you give it a proof, and it tells you whether the proof is correct. So the role of the machine here is to keep track of the state of the proof. It verifies that proof steps are correct, and it gives feedback about what happened when you did a proof step and things like that. And the role of the human is to interactively give commands called tactics to the machine that the human thinks will help the proof go further in the right direction. And then the system will give feedback on these tactics. So just to give you an idea of what it's like, I will give a quick demo. So this is the COCK proof assistant, and what we're going to prove is a lemma called +com, which basically says that for any two natural numbers x and y, x plus y equals y plus x, so commutativity of these things. So we can ask COCK to verify this this lemma, and it tells you, okay, this can be a lemma. In order to prove it, you have to actually show this. So this is the feedback that it gives. We're now having to show this, which is exactly the lemma. So what we do is we give our first command. This goes intros, which says that, well, we're going to take two actual numbers, x and y, and about these actual numbers, we're going to prove the commutativity. And how you do that? You do induction. You do induction on x, which gives us two subcases, one where x is 0 and one is where x is a successor of some number. So let's prove the base case. So what we're going to need is we're going to need to remove these zeros, right? This is almost equal to each other except that these zeros are there. So we're going to use a rewrite on an existing lemma that's called +0n, and it's going to remove one of these zeros. And then we're going to do a rewrite again, and then we're going to do +n0, which is almost exactly the same, and it's I will actually not do what we want because I did it wrong, and this is where the feedback comes in, right? I can see, well, now I got an extra 0, so I'm going to actually have to tell it needs to be the other way around. And now we have two y's, which is just reflexivity now. And then we have proved our first subproof. And for the second subproof, I'm not going to bore you any further, and I'm just going to copy in the actual proof. So there is more rewriting going on and more reflexivity going on. And then at the end of that, the system will tell you, okay, no more subgoals. You've now proved it, QED, commutativity is true. So that's what the system does. It interacts with you in order to get you to prove a lemma. So, oh yeah, and that brings us to the next question. What is the problem we're trying to solve here? This is a more real proof instead of what we just did. This is a proof about real numbers, real analysis, and this is the statement of the proof. It's a theorem. And well, the theorem is not that difficult to understand, but the proof is actually one huge almost 1,000 lines of code that a human wrote himself. And it just goes on and on and on. And this takes many days, if not weeks, to write correctly. And then it takes even more time to maintain this kind of stuff. So the problem that we're trying to solve is that it takes way too many human hours to try to prove these complex theorems. This was still a fairly simple theorem, actually, and it is just too expensive. So what is our solution? We want to give the human a digital sidekick, which we have called Tactician. And the goal of Tactician is to do all of the tedious work for you. So we're not saying that you're going to write this super complex proof entirely automatically. That's not within our possibilities at the moment, but we're going to help you when it's just a bit too simple and you just want someone else to take care of it. So what does Tactician do exactly? It learns on the fly from the commands that a human sends to the COCK proof assistant. And it uses the information that it learns from these commands to synthesize proofs on its own. So every time you use a command, you do it in a certain context, and tactician keeps track of this and learns from this. And then when you ask it to, it can synthesize proofs without you doing anything. So for this, we have a number of components. We have the proof recording, which is the part where you learn from the human. And the proofs that we have recorded, we built a model from them in an online way. So you get immediate feedback from the system. And what you can do then is you can do tactic predictions. So given a current proof that we're having to prove, you can ask for the next command that tactician thinks will be useful to you. And then finally, you can use this tactic prediction to do an entire proof search. So you can build a proof search tree by repeatedly asking for predictions and trying to prove an entire lemma completely automatically. And then we have some design goals with this. We want this to be a system that is really used by actual COC users. So COC is a fairly popular proof assistant, and the goal here is to get something into the user's hand that is actually usable. So it needs to be seamless and completely interactive, no complex machine learning configuration, easy to use, so that everybody can use it, because the experience tells us that if COC users, if it's not simple, then COC users will not use it, because they have they already have a lot of complex things to think about. They don't want to think about complex machine learning. So what is the result? What we've made is a plugin for COC that provides you with two more commands, a command called suggest and a command called search. And suggest basically asks you, tells you, well, maybe you want to use this command next, and search basically tries to prove a goal all on its own. So let's do a little demo of this, and I should know that you can use this, that you can try this demo online without having to install something on this website over here. So I encourage you to try it out. So let's go back to the beginning of our proof here, and let's try the suggest command. The suggest command actually doesn't do anything, because the system hasn't learned anything. We have not input any commands yet. So we first have to do some commands, which we already did. So let's do some of these commands again, and let's ask again for suggest now. And now it actually gives the suggestion reflexivity, which is exactly what we need. So it has already learned immediately from the few commands that we've given it. In practice, we will, of course, give it much more commands, but this is to give an example. But what we actually want to do is we want to have it prove the next lemma. The next lemma is the associativity of plus. So basically the ability to change the parentheses around when you have three things that you want to add together. So here again, we can ask for suggest. And it actually gives us two tactics to try. You can either try index, intros, or induction. Well, this is actually not such a bad suggestion. You can do intros and it will work. As you can also do, you can again ask it for another suggestion. And then it says, well, intro you already did, but maybe try induction again. And that will all work. And this will help you basically select the right tactics. But you can also just say search, and then it will find the proof, and it will immediately say no more subgoals, and then QED, and we're done. And it even tells you, well, we found a proof, and this is the proof that you would have to type manually if you were going to do it by hand. So this is what tacticians saved the user from doing over here. So that could be quite significant if you're looking for time savings. So then the next question you will probably have is, how good is this actually? So what we did is we did an evaluation on the standard library of the COC proof assistant. And this is basically a big library with all the lemmas that everybody needs. So lemmas about numbers and real numbers and lists and all kinds of things like that. And there are about 11,000 lemmas in there. And our best current machine learning strategy, we have quite a few, but the best one currently can prove 37% of the entire standard library without the human having to do anything. So it proves the 37% of the lemmas from start to end without help. If you do some kind of in between some of it is done by the user and some of it is done by a tactician, then it will become much higher. Yeah, so those are our results. System is called Tactician again, and we have a website, and on the website you can try it out. Please do that, and please give any feedback that you have. We're always curious about the users and did it work, did it not work, things like that. And are there any questions?
Thanks a lot, Lasse. One very quick question. We are out of time.
I would have one. Can I?
Okay.
Sorry for possibly naive questions, but maybe we are trying to prove something and we know that it doesn't work in some more general case without some assumption which we have, so that we know that the proof cannot be done without this assumption, and it was not yet used by the prover. Does your system allow to say, yes, please, this is an assumption which must be used somewhere in the proof, so keep this in mind and try to use this knowledge?
Yes, so if you have, for example, some lemma that you have not yet proved, but you know that it must be true and you know that it must be required, then you can basically tell it, well, I haven't proven this yet, and you and tactician has also not proven it yet, but I know it to be true, and I'm just going to give it to you, and then the system can indeed use it. Yes.
Okay.
Thank you. My question was even simpler because I asked of assumptions which are used, which are known to be valid, and just were not used so far, and we know that they are necessary.
Sorry, we really have to wrap it up. So thanks a lot, Lasse. Thanks for the question, Mirko. So Thibault, can you share your slides? Do we have Thibault? I saw him.
Yes, hello. Can you see my slides?
Thibault, I can hear you. No, not yet.
Okay.
Well, you are not sharing your screen probably.
Okay. Now?
Oh, yeah, now it's okay. You can go.
Okay.
Yeah.
So my presentation is about teaching program synthesis to a computer. So this work was published at a conference this year. So what do we mean by program synthesis? So we have a set of data and we want to find a program that represents this set. Much like machine learning, but this program has to be expressed in a concise way. So here we have this data, these numbers 4, 6, 9, 10, 12, 15, and we have to decide if a number is a member of this set or not using a function. So we can recognize that this is the list of composite numbers, and we can write a program that tests if a number is composite or not manually. So what we want to do here is to do it automatically. But we will not choose standard programming language. We will choose to represent it using a formula, mathematical formula. So we'll say that k number k is in the set if there exists x and y natural number, such as k equal x plus 2 times y plus 2. So this is another way of expressing a program. So now, why should we teach program synthesis to a computer? So first of all, we have a more efficient classifier, for example, than a neural network classifier. Usually, a program can be executed faster than running a neural network. And the second most important thing is that it allows for mathematical reasoning on the concept you just realize. You just discover composite numbers. Now you can reason about composite numbers. So in the end, a robot can make better and faster decisions. So now how we did it? So we train a neural net, our system, first we need to generate some examples, problems to solve. So we first generated some random polynomials and until we got 2,000 problems, 2,000 different sets that we need to find a polynomial for. So basically we will forget about the original polynomials and now we are trying to rediscover one polynomial or one program that would match the data. So first we need to transform this into a game. So we have a state of your game and you have to choose how to build your polynomial gradually. So we build the polynomial from left to right, and then we so we choose each time the next token, and so that defines our search space. So given the search space, we can employ an algorithm, search algorithm such as Monte Carlo tree search, and explore the different paths, and we can find a solution or not. At the beginning, we have a random guidance, so it's basically a random search, so it's very unlikely to find a solution, but it finds some solution, and then we can do some training, and using this training, we can guide the search further. We use tree neural networks to do the guidance, and the guidance consists of creating embeddings for formulas, and then computing a value, which is how good we are doing, and a policy which move to choose in the game. Finally, the results we get is at the beginning, we can see that we solve almost nothing, but we can still learn a bit, and then we gradually solve more and more until after 100 generation of this loop, we get to almost all the problems solved. A more interesting analysis might be to look in depth into the coefficients or the solution produced by the algorithm. So it's very not random. So it really exploits patterns in the data and figure out that 7 it should be a very good coefficient. And figures out that maybe you don't need to have odd exponent as don't need to have as much odd exponents in variables. So this is demonstrates that it's a kind of creative way of thinking that it like comes up with its own solution. Moreover, it's kind of general. The framework is kind of general. It works on any game specification. So we also use this to do the same work, but for Combinator Synthesis, which is about the Combinator SKI. And we show that it outperforms the state-of-the-art ATPs to synthesize combinators. Thank you for your attention.
Thanks a lot, Thibault. One quick question. All right, if there are no questions, then I think we are just on time. So thanks to all the speakers, and I'm handing over the session to Zdeněk.
Okay, thank you very much. And it's our turn now. So let me share my screen for a minute. So Industrial Informatics Department performed quite well last year. We had in total like 10 publications in impacted journals. Some of them have been published already last year, and some of them have been just accepted but not published yet. So you see them on the screen, hopefully, and the ones marked with asterisks will be presented today. So maybe I can mention that we also had some other publications related to scheduling of wireless sensor networks by Claire Hanen and Asim Ahmad. And then we had also some paper by Přemek Šucha and his collaborators from France and Italy related to multi-agent project scheduling, and also 2 papers by Anna Minaeva in collaboration with Munich, and 1 survey paper in ACM computing surveys. So this is for journal papers. And as for awards, we have got 2 student paper awards in conferences, and both of them were authored by Ondřej Benedikt as the first author. And we had also 1 prize, 1 Confederation of Industry of the Czech Republic, which was awarded to our result called Energy Optimization of Robotic Cells, the project led by Přemek Šucha, and you see it in the middle of the screen. This is a test bed made by our industrial partner Blumenbecker, and we did optimization algorithm saving energy in robotic cells in process simulated environment. So that's all from my side, and now let me ask Ondřej to start his talk and to present his result, right?
Thank you, Zdeněk. Please confirm that you can hear me and see the slides.
I do. I see it and I hear you.
Okay, perfect. So good afternoon, everyone. It's a pleasure to be here. I'm Ondřej Benedikt, a PhD student at this department, and today I will be talking about some of our results, especially about the application of energy-aware scheduling in production. So the research I'm talking about today started several years ago already, when people from Škoda Auto came to us, reached us, and asked for help. What they needed is actually to lower the energy consumption of their production line. So we were asked to come there, analyze the production line, and come up with some potential solution. What you can see in a figure here is like the most energy intensive part of their production line, where you can see several vacuum electric heating furnaces, which are used for hardening of steel parts of the gear shafts. So we concentrated on this part of the production line, and we analyzed it somehow. So on the top, you can see like 1 week schedule of the line. There are actually 10 furnaces in here. And what is important is that the line or the furnaces are not fully utilized. There are some time intervals here in red, blue, and also a bit green when the furnaces are not used. So actually there is some potential to tweak the schedule a bit and to improve it a bit. What's important to note is that we cannot do much with the processing of the steel parts, because they need to stay in a furnace for some given time, and they need to be heated to like 960 degrees to actually reach the product quality. So this cannot be changed, but what we can do is to somehow manage the behavior of the furnace during the time when it is idle. So we did some analysis, and actually you see one of its results here. So we tried to lower the temperature of the furnace during some idle period, and we observed the results. So when we lowered the temperature from 960 to 600 degrees Celsius, we observed a decrease of the power consumption of the furnace from like 40 kilowatts to about 18 kilowatts. So it can be seen that by managing the state of the furnace, some significant savings can be achieved. But it's not that simple. You need to take into account the time needed for the cooling and also for the heating up and so on. So in our research, we concentrated on a bit simpler case with a single machine only. So we want to schedule a set of jobs on the furnace, on a machine, such that they are all scheduled, and we want to manage the state of the machine during the idle intervals such that the total idle energy consumption is somehow minimized. Note that the jobs cannot be scheduled arbitrarily because they are restricted, like the time when they can be scheduled is restricted by some release time and deadline, by some time window, because the jobs arrive from the previous stage of the production at some time, and also they need to be prepared for the next stage of the production by some other time. So there are some time windows within which we need to schedule them. Our approach for the optimization is decoupled. First, we analyze like the behavior of the furnace during the idle intervals, and based on this analysis, we then do the energy optimal scheduling. So for the optimal control part, it was very, so to say, pleasant collaboration with my colleagues Baran Alikoc here from CIIRC, and also with Sergey Kojimikov from the Academy of Science, both like expert in control theory. So in order to do some control, we needed a model. So we decided to use this bilinear system model described here by this differential equation. This is commonly used in the literature to model like heat-intensive systems such as furnaces. And for this model, we identified its coefficients, its parameters based on the data measured at Škoda. And we wanted to find like the optimal control, minimizing the energy consumption for any given idle period. The result is that certainly there exists a unique optimal control under some mild assumptions on the parameters, which is okay in practice. And actually, this control is quite simple. It's like zero bank control with one switching time after which the furnace is turned on to be heated up. This switching time is implicitly given by this formula. So there is optimal control for this system which we used, which can be used actually to model the behavior of furnace during any idle period, fixed one. And if we enumerate this, or if we solve it for like any idle period, we get this relation between like idle period length and the optimal energy consumption when using the optimal control. So we end up with kind of this function, which is encapsulating like the optimal control. And basically any point here is corresponding to one idle period with one optimal control. And what is interesting is that this function has some interesting properties. Specifically, it's concave, and this concavity will help us significantly during the scheduling phase. So here for the scheduling, as I said, we have a set of jobs and their permutation, and we want to start their start times such that every job is scheduled within its time interval given by release time and deadline. And we want to schedule them such that the total energy consumption during the idle periods is minimized. And another result is that given that the energy function is concave, which it was for our case, this scheduling can be done in a polynomial time. The problem can be solved in a polynomial time. So those are two results. And finally, we verified, we ran many simulations and we compared it with like common approach. So commonly, the state of the machine is modeled simply by enumerating all the possible states of the machine and also the transitions between them. So commonly we have something like this, some graph characterizing the behavior of the furnace. Note that this is not very possible for the furnace itself, because we would need like infinitely many states to model like every possible transition. So here by green, we have like our approach, our energy function. In blue, there is energy function corresponding to this like simpler case. And here on the bottom, you have like simulation results, which are showing that basically our approach dominates the existing simpler approach. So there are significant benefits in like employing the optimal control and combining it with like the scheduling itself. So that's roughly everything from me. Based on this research, there were two publications last year. One was the conference publication, for which we obtained the Students' Paper Award, so it was positively accepted by the community. The other one is this journal publication, Computers and Operation Research. Yeah, so that's it.
Okay, Andrzej, thank you very much. So time is over. So if you have a question, ask it in chat or ask it Ondřej in person, and we will proceed to the next speaker, which is Mařík Velk. So Mařík, if I may ask you to put your microphone on and to share the screen. The floor is yours.
Thank you, Zdeněk.
I hear you.
Hello, everybody. Let me share the presentation.
I see it. That's okay.
Perfect. So my name is Mařík Velk, and I'm going to talk about scheduling in time-sensitive networks. I was working on this project under the contract with Huawei, with the Huawei research team in Munich. It was nice and tight cooperation. So what's time-sensitive networking? So basically, we can say that it's a set of standards whose aim is to enhance classical Ethernet for real-time networks. In this way, we can accommodate highly critical traffic that appears in various cyber-physical systems. These include several domains such as automotive or industrial automation. In these factories, there are several sensors who periodically send data to programmable logic controllers who do some computation and in turn send the data to actuators. So these transmissions of data must meet harsh deadlines, and so in order to achieve deterministic nature, we obey the time-triggered paradigm of the communication. So how is this done in TSN? So TSN switches contain so-called time-aware shaper, which is a mechanism of gates. So basically, at each egress port, there are 8 queues, and each queue is associated with one gate, and the time-aware shaper is actually opening and closing the gate based on the statically computed schedule called gate control list. And whenever a gate is open, the frames are dispatched one at a time from the queue that is open with this gate. And it works on the principle first in, first out. So lurking behind this is a problem, which we refer to as the lost frame problem. So consider this scenario. The blue rectangles are network nodes, and the gray rectangles are transmissions of frames. So, for example, if we consider in this situation that frame of flow number 2 is lost on its way, it can happen that frame number 4 will be dispatched from node X earlier than anticipated. And in turn, it may happen that 4 will be in-queued earlier than frame number 3. So in this queue, from what is going to be dispatched from A to B, we were supposed to have 1, 2, 3, 4, but now we have 1, 4, and 3. However, the frame number 3 was expected to be delivered at 43, whereas now it is delivered at time 47, which means that even when something is sent earlier than anticipated, something else can be delivered later, which can be even after deadline, and it can have far-reaching consequences. So we need to avoid this if we want to maintain the deterministic nature of the network. So we will look at the schedule over several links because we deal with periodic scheduling. So consider, for example, that flows number 2 and 4 have 2 occurrences in the hyperperiod, whereas flows number 1 and 3 have 3 occurrences in the hyperperiod. So we can see that on the link where all of the flows occur, we can see that it almost overlaps here, which shows that even when we consider zero-G restriction, the periodic scheduling is a difficult task. So the description of the scheduling problem, we have 2 kinds of variables. One is the start time that we want to find for each frame transmission, and the other one is QID, where the frame is stored. The scheduling involves several constraints, such as release and deadline constraint. Next, we have resource constraints, which means that the rectangles here, which represent frame transmissions, must not overlap in time. Further, we have precedence constraint, which means that frame from this node can be dispatched after it is fully delivered to this node and processed in the switch. And we consider 2 objective functions. One is minimization of the total number of queues used. The The motivation for this is that we consider only the time-triggered traffic, whereas in TSN networks there is usually many more classes of traffic, and minimization of the number of queues used for the time-triggered traffic allows for better timeliness guarantees of the other classes. Other traditional objective function is minimizing the maximum end-to-end delay, which is often referred to as the response time. And how to avoid the lost frame problem? The traditional approach from 2016 is to use frame isolation constraint, which basically works such that we treat queues as unary resources, which means that cannot be more frames stored in a queue simultaneously. By the other word, one frame, the red frame from here must be dispatched earlier, and then the green one may be in-queued, or the other way around, or the frames can be stored in different queues. Also, we distinguish frame isolation constraint with duration, which is a bit less restrictive. It assumes that the frame is stored in a queue after it is completely received by the switch. But still, it's like the traditional approach used in the literature. So here comes our innovation. What we propose is to slightly enhance the hardware of switches. And it goes such that the switches will check whether they are about to send the right frame according to the original schedule. And if the switch sees that it would send something different, not according to the original schedule, it will be idle instead of sending the different frame than anticipated. So this simple hardware enhancement, which has only tiny little overhead, hardware overhead, only needs to introduce queue order constraint, which ensures that the frames will be dispatched from the queue in the same order as they have been stored in the queue. So what we did in the paper, we formally proved that the space of feasible solutions subject to the new constraint can only increase, and it actually strictly increases. So this was the first contribution. And we implemented the models in integer linear programming formalism. We often use constraint programming using IBM CP optimizer, also satisfiable modular theories using Z3 solver, but this one turned out not to work very well for our problem. So we implemented only the models in integer linear programming and compared the various constraints. So regarding the experiment, we are interested in the success rate, which is the number of scheduled instances under the three constraints mentioned. And we can see that on average, the percentage of scheduled instances increased from 63.7 to 88.5. And if we take a look on the number of used queues, we can also see that it increased, whereas the response time or maximum delay slightly got worse. If you look at the graph that shows the dependence of the number of instances scheduled on the number of frame occurrences in a network, we can see that our novel constraint can schedule much more instances that contain a lot of frame occurrences. And even though the search space increases, we can see that the computation time is still much lower than the traditional constraints. And if we look directly on the average number of scheduled flows, we can see that it increased from 86.4 to 151.2, which is almost 100% lower. So another contribution was experimental validation on real hardware that was performed by Huawei. And all I can say about it is that it included a lot of wires and a lot of gadgets. So to conclude, there were three outputs of the cooperation. The first one was what I was talking about now. It was published in IEEE Transactions and Communications. And the second paper, we developed two novel constraint programming models that solve joint routing and scheduling, which is another option how to increase schedulability and throughput of time-triggered traffic. And this result was accepted in computers and industrial engineering. However, what I consider the main result was the highly efficient scheduling algorithm that is really scalable. We managed to solve instances that contain 2,000 nodes and almost 100,000 frame occurrences in total. but this paper is still under revision in computers and operations research. So that's it from my side. Thank you very much.
Okay, thank you, Mařík. So the same situation, we are just at the time, so I would like to ask the next speaker, if there are some questions to Mařík, please ask them directly or use chat. So Mohammed, please go ahead, share the screen and put your microphone on.
Okay. Can you see my screen?
I do, yeah.
Okay. Hello, good afternoon. My name is Mohammed. I am postdoc researcher in Industrial Informatics Department. Now I'm working on operational research and optimization, application of optimization techniques in manufacturing system, especially concerning the economical aspect. Today, I'm going to talk about a joint research project with University of Tehran in Iran about scheduling in cloud manufacturing system, considering the order rejection or acceptance, pricing strategy, and also equity. This study is published in International Journal of Production Research as a Web of Science and Q1 journal. Let me start with this question. What is cloud manufacturing system? Cloud manufacturing system is a new paradigm for manufacturing under Industry 4.0. As you know, Industry 4.0 is reshaping the traditional manufacturing system to a smart and modern manufacturing. Thanks to advance in new generation of data-driven technology like cyber-physical system, Internet of Things, big data, it would be possible to decentralize manufacturing system to distributed and also integrated manufacturing system. Indeed, there is a pool of resources that are integrated and also interconnected together and are connected to a smart platform. That is, platform is equipped by several decision aiding support system in order to create a harmony between all components in order to satisfy the customer demands. Cloud manufacturing system reduce the cost of system, including the investment cost, operational cost, and overhead costs like monitoring control costs, managerial costs, and or marketing costs. And also cloud manufacturing leads to improvement, the flexibility, responsiveness, and agility of system. In our study, we consider several distributed resources and factories that each factory has one specific owner and is equipped by several type of machine. And also there are several geographically distributed customer. The customer can be individual people or enterprise. That each customer has one job with a specific due date and a specific range of acceptable cost and acceptable price. We're going to decide about the order of which customer will be accepted and order of which customer will be rejected. And second, how to assign the order to the factories and with what price. The pricing is an important decision variable in our problem. And finally, how to schedule the job on a machine in order to maximize the utility of factories and also maximize the utility of customer. The utility of factories is a function of pricing strategy, operational cost, and also the tardiness penalty cost. And the utility of customer is a function of pricing strategy and also the transportation cost. As you can see, we are facing with multi-objective optimization problem. That it would be better that I say the many objective optimization problem. So the problem is not tractable and is not easy to solve by not geometric model and even not by heuristic or meta-heuristic algorithm. For example, the NSGA2 algorithm that is the last version of non-dominated sorting genetic algorithm in base case is suitable for problem with 5 or 6 objective functions. So at first we need to reduce the number of objective functions. For example, for utility of factory, we use this objective function, maximize the minimum utility of factory. This objective function at first reduce the number of objective function, and secondly, establish the equity between utility of factory. Generally, the maximum objective function in base case for them will happen when the value of components are same or very close together. For utility of customer, this objective function doesn't work because the order of some customer will be rejected. Therefore, the value of this objective function for customer always will be equal to 0. For this purpose, we developed another objective function. First and second objective function, we maximize the utility of the summation of utility of customer, and in third objective function, we minimize the utility, the difference between utility of each customer and maximum utility of customers. These two objective functions are also established the equity between utility of customer, but in different way. What about the complexity of our problem? Classical parallel machine scheduling with tardiness objective function is NP-hard problem that has proven in 1998. We also have been proven that our problem is reducible to parallel machine scheduling with tardiness objective functions. So we can find our problem is also NP-hard and we cannot solve it in polynomial time. For solving our problem, we propose an efficient solution method that's called mass heuristic algorithm. Let me back to decision variable of our problem. We have a pricing and also order acceptance or rejection, assigning job to the machine, and also sequence of job. Pricing decision variable is continuous variable and other variables are binary variable. Finding the optimum value for continuous variable when the constraint or objective are linear is easy to solve because just we need to search the corner point and the optimum value exactly is one of them. But in integer programming or binary programming, the situation is very different and very complex. So for this part of problem, we propose several meta-heuristic algorithm like genetic algorithm that can solve the problem very fast but approximately. And for this part of problem, we developed the linear integer programming under an accelerated epsilon constraint method that can solve the problem exactly. Our epsilon constrained method and also meta-heuristic algorithm are integrated together and exchange the information between each other until we reach to high quality solution. What's the meaning of high quality solution? In multi-objective optimization problem, there are 3 important metrics for evaluation of the solution. First, how much the obtained result are close to Pareto optimal front if we consider the dashed line as a Pareto optimal front. Second, what percentage of Pareto optimal front is covered by your obtained solution? And finally, how much obtained solution are uniformly distributed across the Pareto optimal front? The final result of our proposed algorithm in these 3 metrics are really promising that you can find the detail of them in our paper. My presentation is over and thank you for your attention.
Okay, thank you, Mohammed. So if there is one question, we can answer it. Anybody has a question to any of the 3 presentations? If not, then let me ask the last speaker, and this is Jarda Klapálek. So Jarda, please share your screen and start to speak.
All right, I will, hopefully. So can you confirm you can see my presentation?
We do. Yeah.
Yes, thank you.
I hear you. Okay.
Nice. So good afternoon. My name is Jaroslav Klapalek, and I'm a PhD student from Faculty of Electrical Engineering, and I am also the last presenter of IID group. Today I will tell you something about F110 autonomous racing competition, what that is, what is it about, and how it relates to the research we conduct. At first, I will talk about F110 car, which is a scaled-down model of an autonomous car. The advantages of using a scaled-down car compared to the real one are, for example, that this model is less expensive, it is easily modifiable, you put less effort to perform the experiments, and the failures are way less disastrous. On the other hand, there are also some drawbacks, for example, the size of the vehicle itself, as it limits the size of the components. The hardware components of the F110 car are similar to the real autonomous car. We have an onboard computer, LiDAR, camera, and so on. We have built the car from scratch using a Traxa/chassis as a base. Let me note that the components themselves, you can see on the slide, are restricted by the competition I will be talking in a moment. Since we are using a common ARM-based NVIDIA Jetson TX2 running Ubuntu 16, we can reuse all the available applications on the system without having to implement them ourselves. The connection between peripherals and individual algorithms is done via ROS-Kinetic, which is supported on this board. On the image below, you can see a drawing of the software architecture of our F110 car. We divide the algorithms and applications into three main blocks: perception, decision and control, and vehicle platform. Perception block handles communication with sensors, processes their data, and derives additional information from them, such as map of the environment. Decision and control, which stores planning algorithms, path, followers, trajectory trackers, and so on. In this presentation, there is only necessary to distinguish between two of them, the planned approaches, or something that is using map, or reactive or mapless approach. Last block is called vehicle platform, that translates the requests from previous blocks to signals recognizable by the car. In addition, blue lines you can see on the diagram splits the diagram into three different parts. Utilizing the architecture, we can test the algorithms, the middle part, without knowing about the underlying platform. It can be the scaled-down car or a simulator. Finally, we get to the competition itself. Using its full name, International F110 Autonomous Racing Competition is an event organized by the University of Pennsylvania in USA. So far, there were 7 competitions, even though the first one was a little bit more like USA only. List of the competitions can be seen on the right side of the slide, along with the years. These events are mostly collocated with major conferences, such as Embedded Systems Week, CPS Week, IFAC, and IROS. In the F110 competition, the participating teams are composed of members from all around the world, such as USA, Sweden, Poland, Italy, South Korea, and of course, Czech Republic. We have attended 3 of these competitions, and they are marked bold in the list of the right side of the slide. Our biggest achievement is winning the race in Porto, followed by being in the top 3 teams in Torino and later New York City. These competitions were attended consequently by 7, 8, and 10 teams. After our wonderful race in Porto, we have publicly released the approach used during this competition, which was a reactive approach and extension of the follow-the-gap algorithm. Other teams have been inspired by our solution, which led into raising the bar during the later competitions. The competition itself is composed of 2 parts, timed race and head-to-head race. The latter one is quite new, as it was added in the year 2020. In the timed race, only 1 car is present on the racing track. The organizers are measuring lap times of each team, as the team with the lowest lap time wins. Basically, the goal is to drive as fast as possible without colliding with the track borders. In the head-to-head race, there are already 2 cars from opposing teams on the track at the same time. The goal is also to drive as fast as possible, but this time the car overtaking and overall collision avoidance has to be considered. In the video on the slide, you can see a track built during the Porto 2018 competition. This was also the first attempt of head-to-head racing. Unfortunately, we haven't found any opponent. However, one member of the team from Italy, a skilled RC car driver, volunteered to compete against us. On the video, the car that is driving quite stably is ours, while the crazy one is the opponent's. On this stage, we have demonstrated that even a simple algorithm such as follow the gap is capable of this race, even though it is far from ideal. In addition, we were also first ones to demonstrate reliable obstacle avoidance, even though the car wasn't driving too fast. You can see the one that is being crashed right now. Let me note that the manual driving on the floor was really hard, as the floor was very slippery. So even though it looks like that the human operator is not trying, his attempt was actually really good. So even though our reactive approach was successful and adapted by many other teams, it is not enough. This was shown in the Torino and New York competition, where the tracks were built in a way that was trying to penalize reactive approaches. In other words, there was a way to drive through the track even faster that required knowledge of its layout. This is known as optimal racing line problem, which is, in other words, a lap time minimization problem. We have conducted research in trajectory planning using genetic algorithms. Our approach builds upon the state-of-the-art methods, altering the way of trajectory description, which led to overall improvement by reducing the lap time of the same number of genetic algorithm generations. This can be seen on the graph at the bottom of the slide, where our approach is marked blue, while the opposing approach is marked with red color. Comparing the best solutions for the same parameters, our approach is able to achieve lower lap times due to exploitation of turns. Our solution has bigger curvature, which allows the car to drive faster. This is shown on the picture of the bottom right corner of the slide. Along with the active research, we work with bachelor and master students on fast trajectory planning, as the car is moving fast, precise trajectory tracking, as we are able to navigate the given trajectory without colliding with the environment, reliable obstacle avoidance to trigger replanning or reactively navigate around sudden obstacle, complex evaluation of planners to compare solutions among each other, and migration to ROS2. It might seem that these topics are already solved many times. However, our focus is on real-time and CPU undemanding solutions, since we are working on a platform with limited resources that is, at the same time, driving really fast. In the future, we would like to move towards the real scenarios by exploring the scale-down traffic. One of our students is working on a planner evaluation which uses real-time traffic data obtained by image recognition, as you can see on the video. And this is all for me. Thank you for your attention.
Thank you very much, Jarda. And now we have like 2 minutes for questions. So anybody wants to ask something? If not, so let me ask. So Jarda, this competition, the next round will be, I think, in Prague, right?
Yeah, it should be with IROS 2021 in Prague, but since the conference is online, we are discussing whether we could at least make the competition here, even though the conference is not here. But it's still like a dream or a plan to do.
Okay, so the chairman of the conference is Dr. Přeučil, so I hope that he hears me and that he will help us to make it like in CIIRC in presence of at least European teams or teams that are not so far.
I think that it mostly
like
depends
Germany, Italy and Poland, so that we have at least a European, Central European competition. Okay, so thank you very much for your presentations, and now let me hand over to Professor Vladimír Kučera, and he will tell us something about scientific management of platforms and about like a project. We see your PowerPoint presentation.
Can you? Hello, everybody. Can you see my screen?
Yes, we do.
Okay, thank you. So let's start. Again, hello, everybody. My name is Vladimír Kučera, and I'd like to present the results of the Department of Research Platforms, or PLAT, which is the CIIRC instrument to foster the horizontal collaboration among research groups within CIIRC, jointly with RECAIP, which is the Research and Innovation Center on Advanced Industrial Production, a project funded by Horizon 2020 program and the Operation Program on Research, Development and Education. So here are the members of the PLAT department and the results achieved last year. You see the total of 28 results is to be uploaded to the database. For today, for the presentation, we have selected 3 contributions. The first one will be a report on the achievements of the RECAIP project. The second one will concern smart, resilient cities. And the third one will be about decoupling with stability. So I'd like to now invite Dr. Tilman Becker to make the first presentation.
All right, thank you very much. Let me share my screen. Can you confirm that you can see it?
Yes.
Thank you.
You can see it.
So let me talk about RECAIP and say a bit about the background also. As you will know, it's a collaboration between Prague, Brno, and Saarbrücken in Germany. The goal is to set up a new center of excellence in the area of advanced industrial production. So it's AI and robotics as one of our foci. It's hosted here at CIIRC and it has partners in Brno at CETEC, the Brno University of Technology, and in Germany at DFKI, the German Research Center for Artificial Intelligence, and the Center for Mechatronics and Automation Technology. We have a large amount of funding to spend over the next years to set up the center, mainly from the European structural investment funds and also directly from the Commission for setting everything up. It's distributed between the partners, with CIIRC being the main beneficiary, and the core investment will go into machines and hardware for the respective testbeds. In terms of what we've achieved so far since its introduction in September 2019, we've started institutionalization. So we've set up a large set of documents describing how we want to proceed, how we want to conduct research. Very importantly, set up tenure track positions and the according policies within CIIRC to guide their career developments, and set up a grant lab strategy in cooperation with the excellent project management office we have here at CIIRC. It's of course setting up the infrastructure that's ongoing and will only be completed within this year. So we have the full test beds equipped with all the new machinery and start the actual scientific research we are very much looking forward to. A bit about the hardware. We're setting up robot production cells, connecting conveyor belts, different robots like Delta robots, human-robot collaborative robots for other fields than production, for example, in gastronomy, 3D printers, and also we're setting up an autonomous warehouse with mobile platforms, so we can really mimic an entire factory as well as possible within the testbed. And there's more, there's machining. So there's laser welding cutting machines, this big monster hybrid machine that combines additive and subtractive manufacturing, metrology for quality, of course, control, of course, but also for checking the results of simulations and optimizing digital twins. And the research areas that will be covered there are at least the following multi-agent systems for planning of production at very different levels, just the machine, the entire site, and also distributed production between the partnering testbeds. This all is modeled in digital twins or digital shadows, mirroring the production data, allowing state analysis, evaluating different scenarios, and so on. It's about dynamic models of machines for diagnostics and optimization, and of course distributed production. How can we collaborate with other test beds? In terms of setting up the scientific capacity, which was really the focus in the last year, it's setting up these new research groups with the tenure track positions and establishing the Grand Lab strategy. These four researchers that we've been able to attract to CIIRC are presenting here already. It's Torsten Sattler, Tomáš Mikolov, Mikuláš Janota, and Martin Suda, probably in inverse alphabetical order of first name, with very different fields, and it'll be an exciting time to see how their fundamental research is applied within the testbeds. In terms of overall progress, we have a strong international collaboration based in the Czech Republic on the collaboration with the National Center for Industry 4.0, but we're building it up with a strategy towards the European Digital Innovation Hubs together with the German partners who have a parallel proposal. And within the Czech Republic, we're joining with the Technical University of Ostrava to get onto the large research infrastructure roadmap, which will eventually hopefully become a European endeavor. There are some KPIs, and I've picked one that's quite telling about the great progress that's being made, which is are we applying for projects, and overall we're doing very well, and you can see that CIIRC is really the main partner in this endeavor. The very high numbers are a bit misleading because we're participating in EIT manufacturing, which has many smaller projects. So it's about building this collaboration with other partners as a joint AI ecosystems with industrial partners, and very importantly with the European associations CLAIR and ALICE. And we already see recognition of what we're doing. So we will see a European-American workshop on advanced manufacturing with the University of Berkeley and MIT. And for example, Professor Mařík was invited to become a member of the European-Japan Business Forum. So we're trying to do work in outreach quite successfully. Also, last spring, out of the testbed, we saw within just 1 week the designing and 3D printing and releasing the plans for the respirator, which has received a number of awards, and you can see with Dodgegal here receiving one of them. This is something we're very proud of, and I think this has been very helpful and positive work. We're doing outreach to the general public, to industry partners, and most importantly in science. So we're organizing, co-organizing, and participating in various workshops and conferences. The very latest news, last week's Hannover Messe, which was celebrating 10 years of the concept of Industry 4.0, had a presentation jointly between CIIRC and DFKI in the main track, with a round of discussion afterwards with Professor Walste, who's one of the founders of Industry 4.0, and Professor Mařík. And also last Thursday, we had a very successful review meeting with the European Union. So we're on a very good track as recognized by the EU. So what are we doing next? We're setting up the ground so far. Now the next point is strengthening scientific excellence and make use of the upgraded testbed facility. There are very exciting new calls from the European Union for testing and experimentation facilities that we hope to participate in. Working on a national center for AI is a possibility. So you can see there are a number of exciting opportunities for research and outreach and new applications in this year. And thank you for your attention. I hope I stayed within the time limit. But I'd be happy for questions.
Okay, thank you, Tilman, for your nice presentation of the impressive results of the project. I plan to leave some time for questions at the end of our presentations. So, okay, I'd like now to invite the second speaker, Sergey Kojimikov.
Can you hear me?
Yes.
Oh, great.
We can hear you and we can see your presentation.
That's perfect.
You have the floor.
Thank you. Thank you. Greeting to all participants, and thank you for joining. I want to present you the results of our project, Multi-Agent Approach for Smart Resilient City, and explain how we want to create a smart city framework that can be resilient by design. Having 10 years experience working in smart manufacturing and Industry 4.0, we have taken the same principles of service-oriented, holonic, and multi-agent systems and applied them for the smart city concept. So maybe you will find our experience interesting. In previous years, there was a trend for smart sustainable cities, and now, mostly because of COVID, there is a new trend for smart resilient cities. In our work, we author a new concept of ICT framework that is resilient by design. For this, it should operate as a digital ecosystem of smart services. We have made a research that showed that to create a smart resilient city, we need to use network-centric system of systems, manage the flow of resources. We need to manage the produced data. We also need to use unified knowledge base and ontologies and implement interoperability for city services. Pretty the same principles as for Industry 4.0. So we think that the smart resilient city framework should be based on the unified semantic space and methodology of complex adaptive systems, where each part can operate entirely autonomously, but also able to interact and negotiate with other elements and make consistent decisions with other systems. How actually it is working right now? We have different elements and solutions for smart city. For example, living in Prague, we have Volt, Lime, taxi, field services like garbage construction, state services like public transport, police, ambulance, energy providers, and many others. And they're working pretty separately and independently. So developed in different software languages and different software architectures, all those solutions. And the general idea is to create a smart city framework that is based on the city ontology, multi-agent engine, and data platform. And it should enable interaction between different city elements and city services. It will help to achieve the cooperative work between them. For example, between food delivery, taxi services, mobile field services, transport, energy systems, and others. How we can achieve that? We have described every component as a producer or a consumer. As a consumer, it can have demand or several demands, and another element can be a producer. The idea is to find the link between them, to join them. So every element in the system wants something or provides something. So we want to collect all resources and demands in one cloud and match it. For this, we use a multi-agent approach, where all the producers and consumers are represented by software agents. This multi-agent approach helps to achieve the general resource demand virtual market. On this slide, you can see the agent negotiations in the energy model. It finds the optimal balance between the reasonable consuming and smart efficient production. Most of the smart city concepts rely on creating one unique database and provide access for the city services. Instead of that, we have developed the ontology-based model that can specify main objects like buildings, roads, bus stops, traffic lights, energy sources, environment, and many others. Those objects can have a detailed description. For example, building can be a restaurant or a business center or a living building. It can have, has like different attributes like number of floors, date of construction, and others. And the ontology can also describe people, their activities or requests and requirements. In general, now we're working in the area of artificial intelligence called emergent intelligence or swarm intelligence. It helps to achieve the synergy between various subsystems, transportation, logistics, safety, security, energy, administration, etc., with reference to the quality of life of citizens. You can also see not the full list of our publications on this slide. To prove the approach and achieve the cooperation between different actors with different KPIs and sometimes contradictory aims, together with other HVUT faculties, we have developed the Smart City simulation software for modeling, planning, and strategic assessments of urban areas. Now it combines 4 micromodels: transport, energy, urban morphology, and environment. And the aim is to show the real situation in the city as a set of city KPIs, check the city stability, and show the possible reaction of city services for different disturbing impacts. The framework development process was divided into two main steps. The first step, we want to create a smart city simulation software. The second step involves the full integration of all services in one dynamic, adaptive, real-time digital ecosystem with resilient properties. And the conceptual architecture of the first step you can see on the slide. So we took four and forced them to work together. On the slide, you can see the system user interface. You can see four models: energy, mobility, urban morphology, and environmental model. All four models working together and connected by sets of KPIs. You can change the transport model, for example, implement the quarantine case when everybody is sitting at home, and see how it will influence other models, for example, the energy situation in the city. You can implement other cases, for example, virtually create the new shopping mall and check how it will influence the area around it in case of environment, mobility, and energy. On this slide, you can see different city projects, for example, secure building on Vytezni and Amnesty, or changing of transport and around Davidska. So in general, our system can answer the questions how it will influence the mobility, ecology, and energy situation when those projects will be completed. On this slide, you can see in details dust model in case of new transport infrastructure around Davidska area. And on this slide, you can see how the new Borzyslavka Centrum, when it will be completed, will influence the transport, energy, mobility, and environmental situation. Environment in case of PM10 dust particles, but also can be other parameters like thermal comfort or small dust or others. As the next step, we plan the deep integration between the models. The strategic target is to build an urban virtual model playing the role of kind of digital twin of the real city area. In it, the economic, environmental, and social parameters are combined with common synergies among different actors. Also want to achieve resiliency by design, where all city elements work together as one digital ecosystem. My presentation is over. Thank you very much.
Thank you very much, Sergey, for your very interesting presentation. We shall allow questions at the end of the block, okay?
Yes, sure. Thank you.
So let me now take over and present my own result. The topic I'd like to present is a result on decoupling of systems with many inputs and outputs while assuring their stability. What really the decoupling is? This is a problem of compensating a system with many inputs, many outputs in such a way that each system output can be independently controlled by a single input. This means that the internal couplings are neutralized and the transfer matrix of the system is diagonal and non-singular. Such a structure is, of course, desirable in many applications. And the decoupling compensation chosen to achieve the decoupling is the static state feedback. Here is a brief account of the history of the problem. This is indeed a long-standing famous problem of control theory. The earliest known investigation of system decoupling dates back to the 30s. And all past solutions, there have been many to be sure, were obtained under restrictive assumptions on the system or on a particular form of the control law. The first unrestricted solution was achieved by myself in 2017. The problem, however, is that the decoupling feedback may destroy stability of the system. And a complete, stable decoupling solution was finally achieved last year. The main issue is the following. if the system is first decoupled while ignoring stability, then stability is lost. Of course, the system can be stabilized afterwards, but it may not be possible to restore stability while maintaining the decoupled structure. So the solution is to stabilize the system first and then decouple while preserving stability. The key step is to bring the stable system to a certain standard form by the transformations which are admissible while decoupling, namely stability preserving state feedback and input and state coordinate transformation. This is done by bringing the transfer matrix of the system to a special form, Hermite normal form, over the ring of proper and stable rational functions, and then realizing the effect of the transformation by state feedback. I am going to explain all this by means of a very simple example. Suppose we are given a system like this. Here are the matrices ABC. The system has 3 states, 3 inputs, 2 outputs. And we seek a state feedback control law of this form. Therefore, we seek the matrices F and G such that the closed loop system will be stable and with diagonal transfer matrix. So let's first decouple the system while ignoring stability. So we bring the matrix, the transfer matrix of the system to Hermite normal form over the ring of proper, not necessarily stable rational functions. So here is the transfer matrix of the system. Here is the transformation which brings it to the Hermite form. We also apply this simple state coordinate transformation to obtain the decoupling standard form. Here is the block diagram of the system, 3 inputs, 2 outputs, 3 states. The decoupling feedback in this case is simple. I would say trivial. We just disregard the 3rd input and we have the system decoupled. The transfer matrix of the system is 1 in the first channel and 1 over S in the second channel. 1 over S is a pure integrator. But when decoupled, the system, unfortunately, is not stable. You see, this is the pure integrator is not stable, and this is really unstable. Of course, the system can be subsequently stabilized, and here is an example of a stabilizing feedback. But the transfer matrix of such a stable system is no longer diagonal. So we lost the decoupled structure because of this off-diagonal element. And when we follow here the second channel, the green path, okay, connected to the first output. This is, okay, the problem. So the system is no longer decoupled. So the solution is to first stabilize and decouple while preserving stability. We bring the system again to this form, but now over the proper and stable rational functions. So again, the transfer function of the plant, some transformation which leads to this form. And the block diagram now looks like that. There are again 3 states. The system is stable. And the stability preserving feedback which decouples the system is shown here and also here in blue. The feedback compensates for the undesirable coupling while this one, while maintaining stability. You see, this path from input 1 to output 2 is compensated by the blue connection and also this one, okay, to make this element 0. So the feedback, the system is stable and decoupled. On the theoretical side, the existence of stable decoupling solutions is conditioned by system invariants with respect to the group of admissible transformations, and they all are shown in the special decoupling standard form. These are controllability indices of the unobservable subsystems, orders of finite and infinite zeros that occur in each diagonal element, and orders of finite and infinite poles that occur in each column of the inverse of this matrix. The solvability conditions are necessary and sufficient and have the form of inequalities, very simple conditions among the lists of non-negative integers, because the invariants are non-negative integers only. The result was published in the IEEE Transactions and Automatic Control last year in electronic form and will appear in printed form this year. I was quite happy to see that the reviews which were obtained for this result were very, very favorable. So this is the end of my presentation. And I am back. Can you hear me?
Yes, we do.
Okay. So I'd like now would like to allow time for questions. All the three of us, Tilman Becker, Sergey Kojimikov, and myself, will be happy to answer your questions. No questions? Okay.
This is usual.
Oh, yes, of course. This is because the presentations were excellent.
This is the only explanation.
May I ask a question? Yeah.
Oh, yes.
Question is to Vláďa Kučera.
Yes.
You know, it's long time I studied control engineering, but your solution seems to me, after the short presentation, to be obvious. How come it took 80 years to get it? Why the other people didn't do it?
I will explain. This was a very, very simple example. Therefore, the solution, when already found and known, seems very intuitive and simple. But this is not really so. You remember the blue and green paths in the system. It would be very difficult to intuitively design such a feedback. Some partial solutions were known for quite a time, have been known for quite a time, but only for systems with the same number of inputs and outputs, and for the so-called regular state feedback. The general solution presented in my presentation is valid for systems having more inputs than outputs, so that we can afford to lose some inputs and use part of the dynamics of the system to decouple, and therefore the possibilities for decoupling are much larger, and therefore the range of applications is possibly larger.
Okay, thank you for the explanation.
Okay, gentlemen, so thank you very much for your presentations.
I think we have the raised hand. Sorry for interrupting. I think we have the raised hand from Lenka Hotka.
Thank you very much, Sergey. I had one short question to Tilman. I would like to know what is your vision in ReCAIP concerning the human-machine interaction, because I am on the side on the cognitive science and the human research. So how to merge these two areas?
Thanks. That's a wonderful question. We are mainly working in the area of human-robot collaboration, in particular with the colleagues at the FKI. And the whole point of that exercise is not to have robots replace humans, but really work as an augmentation, as an assistant. And that needs a lot of communication between human and robot, but in particular, if people are working in teams, also between humans in the context of that collaboration with one or more robots. So all of the areas like the chatbot conversations that we've seen, and in general, human-robot or human-machine interaction apply in these areas. So this is a very important aspect to us.
Okay, ladies and gentlemen, thank you for your discussions. Tomorrow we will continue with the remaining groups, namely robotics and machine perception, industrial production and automation, cognitive systems and neuroscience, and biomedical engineering and assistive technology. So we will start at 1 p.m. and thank you for assisting today and tomorrow as well. Thank you. Bye-bye. I believe that in 20 years we will laugh on this video when we will see it, how young we were, how chubby guys we have been, and so on. Okay. So here is tomorrow.
I appreciate the possibility to present our results.
Yeah, me too. Bye-bye. See you tomorrow at 1 p.m.
Thank you. Bye.